Hello all, my name is John McCarthy and I'm a first-year PhD student in the Integrated Photonics group here in Tyndall. How this presentation is going to go is first I'll run through a few laser fundamentals with you, then I'll talk about some of the objectives of the group and why, and then I'll finish with some analysis of laser designs in the form of simulations, and I'll follow up with showing corresponding characterized results. So, what are lasers used for? Basically, light waves can transmit more information per second with a stronger signal. And in today's day and age, hundreds of lasers are used in modern optical networks, some of which are displayed in the above image. Ultimately, lasers are quite attractive when it comes to high-speed telecommunications. The photons produced by laser depends on the materials used to make it. Here's a rather simple example of a quantum Wall structure in the cavity of a laser. When a forward current is applied, the electrons will flow along the conducting band, holes will flow along the valency band, and are confined in the quantum Wall structure that is created by the double heterojunction. Electron-hole recombination occurs, and a photon is emitted with a wavelength equivalent to that of the band gap energy. So, imagine the cavity of a laser itself as a cavity with a reflective surface at either end, which is used to confine the photons. Depending on the wavelength of the photons produced and the cavity length, the reflected photons will either interfere constructively or destructively. After one full oscillation, the photon will travel a distance equivalent to twice the cavity length. If this distance is an integer multiple of the wavelength, then the wave undergoes constructive interference. If not, it will undergo destructive interference and will be cancelled out. So only certain wavelengths can be supported by the laser cavity. So, the objective we want to explore today in this presentation is to design a laser that will produce a single mode and tunable wavelength. So what does this mean? Well, whether or not a laser is single mode depends on its side mode suppression ratio. This is attained by plotting the power of the laser spectra in dBm and measuring the power difference between the dominant mode of the spectra and the secondary mode. This value is measured in decibels. So if this value is 10 decibels, then the dominant mode is 10 times more powerful than the secondary. If it's 20 decibels, then it's 100 times more powerful. And if it's 30 decibels, it's 1,000 times more powerful. For a spectra to be considered single mode, we require the SMSR to be 30 decibels or greater. So let's first consider a rather simple laser design, the Fabry Perot. This consists of a cavity with two reflective surfaces at either end. The light produced in the cavity bounces back and forth, forming a standing wave. The output mirror will always transmit a constant fraction of the light while reflecting the rest back into the cavity. When designing the devices, I use transmission matrices to determine what wavelengths can be supported in the laser cavity. The two types of transmission matrices that I used describe the transmission through the reflective surface by taking into account the change in refractive index, and the other describes the transmission through the waveguide by taking into account the length of the cavity, the refractive index, and the wavelengths generated. So in the case of a Fabry Perot, you can find the transmission matrix by finding the dot product of two reflective transmission matrices and the transmission matrix of the cavity. The reflection profile is then T21 over T11 squared, and this can be plotted as a function of wavelength. So here's an example of a reflection profile for Fabry Perot. As you can see, the plot is made up of multiple peaks where the maximum reflection coefficient represents the wavelengths that are confined in the laser cavity. As one expects from a Fabry Perot, one wavelength doesn't dominate over the other. However, in an actual experimental spectra, you would expect a certain range of wavelengths to be amplified by the gain media. So let's look at this experimentally. Here's an image of a typical experimental setup we have in our group. The device itself is placed on the probing station and is viewed through the digital camera. The power sources supply the current, and the optical fiber measures the output of the device. The power of the device is measured using the power meter. Here's a close-up of the probing station itself. The device is placed on the chuck, and you can see the optical fiber to the left. So when we're probing the device, we view it through the digital camera. Here's what we would see. The probe is placed on the large contact pad you see to the bottom, and the optical fiber is used to collect the output of the device. Here's a typical spectra of a Fabry Perot. As you would expect in terms of side mode suppression ratio, it's almost non-existent, maybe 5 decibels at most, but you do see a certain range of wavelengths being amplified, but this is caused by the gain media itself. So for telecommunications, it's ideal that the device is single mode. An easy way of achieving this is by creating a mirror region that has slots etched into the ridge. These slots are etched to a point above the active region and act as reflective defects along the ridge of the laser. By biasing the slotted region of the device, a single mode spectra can be produced, and by varying the current across the region, the lasing wavelength can be varied. So here are 2 examples of such reflection profiles. The first, again, shows the reflection profile of a Fabry Perot with a cavity length of 800 microns. As I described earlier, it's made up of multiple peaks where no peak dominates over the other. However, we want to produce a single mode. So, as I mentioned before, we achieve this through introducing slots along a portion of the ridge of the laser. In the below example, we have an 800 micron gain region without any slots, followed by a slotted region of 8 slots with an interslot distance of 108 microns. This results in the maximum reflection coefficient created by the modes of the Fabry Perot region, or gain region, to be suppressed by these larger modes created by the slots. A single mode wavelength can result at any one of these larger modes, but whether it lasers here or not depends on the position of the smaller modes within. By changing the current through this region, there is a change in the effective refractive index of the device, and so, as a result, there's a change in the optical path length. So by changing the current through the slotted section, the position of these larger modes can shift along the spectra. When one of the smaller modes reaches the center of the larger mode, it would have achieved its maximum reflective coefficient, dominating over the other, and will lase at this wavelength. This is more clear if we plot the image in dBm. This creates like a log scale compared to the reflective profile as defined by this equation. As you can see, we would expect one wavelength dominating over the other with a suitable side mode suppression ratio. Let's look at this experimentally. So this is a 2-section device. To the right, we have the gain section, which is like a simple Fabry Perot, but this is connected to another solid section made up of 8 slots with an interslot separation of 108 microns. The output of the light is collected using the optical fiber to the right. So here's just how the 2 spectra is attained. The red is the experimental spectra and the blue is the simulated spectra. As you can see, we do get good agreement between the wavelength attains and the other modes it generates. So what we did was we swept the current across the gain region from 20 milliamps to 200 milliamps, and we swept the current across the solid region to 20 milliamps to 100 milliamps, and we measured the corresponding side mode suppression ratio and wavelength. In terms of SMSR, we attained a maximum SMSR of 35 decibels, but we also attained multiple other wavelengths with an SMSR of 30 decibels or greater. This image shows the different wavelengths we attained. We attained 9 different single mode spectras across a tunable range of 27 nanometers. So you could say at this point that we achieved our goal. We attained a single mode laser, or a laser that produces single mode spectra that had a tunable wavelength. The one issue I would have with this is that it took a large amount of current to achieve these other wavelengths. It took, as you can see here, a range from 20 milliamps to 200 milliamps. Now, what we would rather is if these devices were much more sensitive, as in we'd rather this all happen between, let's say, 20 milliamps to 100 or even lower. But before I move on to that, we can just quickly compare what we attained here experimentally to the theoretical values. And as you would expect, the laser lays at the center of the larger modes of the reflection profile shown in blue. So let's try another laser. This laser design is called a 2x2 MMI laser. MMI stands for multi-mode interferometer. So how this works is, let's say we simulate or pass current through arm 1. So light is generated through arm 1 and it propagates through the MMI. What the MMI does, it splits light equally between arm 3 and arm 4. Now ultimately we measure the output of the device through arm 3. However, if you can see at the end of arm 4, there's this large square pad almost. This is what is called a metal-etched facet, and it is used to reflect light back into the MMI. As you can see, there are similar structures at the end of arm 1 and arm 2. So I'll just go through that again. Let's say light is generated through arm 1, it goes into the MMI, it's split into arm 3 and arm 4. Light is reflected from arm 4 back to the MMI, and the light propagates through arm 1 and arm 2, and so on and so on. And the output is measured through arm 3. Now, the simulation of the reflection profiles of this device is much more complicated. I won't go through it entirely in this presentation, but if you are interested, you could email me after. So the idea was we have a constant current passing through arm 1, and then we can vary the current across arm 2 and arm 4, and in extent vary the optical path length. Now, through simulations, we can see how this would affect the spectra of the device. We can see by varying the length of arm 2, we can change the position of these larger modes that have been created to divide the device. But whether or not they lays at these wavelengths depends on how we vary the length of arm 4. So if you can see by the plot to the right, it's made of smaller modes. These shift along the larger mode, and once they reach the top, then they'll have a maximum reflection coefficient, and they would laser this wavelength. Excuse me. So again, we can plot this simulation in dBm, and as you can see, we attain significant mode hopping by varying the length of one of the arms by a fraction of a nanometer. So ideally, we can think that this would be more sensitive than the slotted Fabry Perot. So again, we test this experimentally by probing it as so. And here is the measured side mode suppression ratio and wavelengths of the device. Now, we attained a side mode suppression ratio of 30 decibels, which isn't as good as the slotted Fabry Perot. However, we attained this by just varying the device from 5 milliamps to 50 milliamps, and across both arms of arm 2 and arm 4. And we also achieved significant mode hopping, attaining 4 or 5 different wavelengths. Here again is just the simulated spectra plotted against the experimental, and as you can see, there is good agreement between the two. So I'll move on to our final device. The idea again is to produce a laser that would produce a single mode wavelength, a tunable wavelength, and would be rather sensitive in terms to current applied. So here we have a 1x3 MMI laser. It works similar to a 2x2 MMI laser, except it only has 1 input and 3 outputs. So as light is generated from arm 1, it passes into the MMI. It's split equally between arm 2, arm 3, and arm 4. Arm 2 and arm 4 reflect light back into the MMI, and so on. And the output is measured through arm 3. So the idea here is to have a constant current passing through arm 1 to generate the light, and then we can vary the reflectance by changing the current through arm 2 and arm 4. So what's different this time with the reflection profile is we found by just varying one of the arms of arm 2 and arm 4, we can change both the position of the larger modes and these smaller modes within. Whereas in the 2x2, we'd have to vary one arm to change the position of the larger modes and vary the other arm to change the position of the smaller modes. So by just varying one, we'd already imagine we'll produce more wavelengths, as would be more sensitive here if we vary both at the same time. This is the spectra in dBm. Once again, we attain significant mode hopping by just varying the length of one of the arms by a fraction of a nanometer. So we characterized it again, and here was the map of the sidewall suppression ratio and wavelengths attained. So we varied the current again from 5 milliamps to 50 milliamps through both arm 2 and arm 4, and we trained this time a maximum SMSR of 36 or 37 decibels, and with a much larger wavelength range. Just quickly, here's an example of how the simulated spectra corresponds with the experimentally attained wavelengths. As you can see, they mode hop in order as is shown across the black dotted line. And here's the image of the different wavelengths attained. Once again, we attain 9 different wavelengths, but across a smaller wavelength range, and with using much less current than the slotted Fabry Perot. So already we imagine this device is much better than the slotted one. Once again, here's just the experimentally attained spectra plotted against the simulation spectra. And as you can see, the modes match up and there is good agreement between both. So just a quick summary. First, I showed you how we characterized a simple Fabry Perot along with the simulation spectra. As we determined, the side mode suppression ratio was almost non-existent, maybe 5 decibels at maximum. It didn't have a tunable range and it didn't have a biasing range. So with the slotted Fabry Perot, we attained a higher SMSR of 35 decibels, attaining 9 different wavelengths across a tunable range of 27 nanometers. However, this required a biasing range of up to 200 milliamps. Next, we tried the MMI lasers. With the 2x2 MMI laser, we attained an SMSR of 30 decibels. However, we only achieved 4 wavelengths across a tunable range of 12 nanometers. And finally, we tried the 1x3 MMI laser with a far higher SMSR than the others at 30 decibels, attaining 9 different wavelengths across a tunable range of 27 nanometers. So that is all. Thank you.